Okay, welcome to the very important part of Laplace transforms, that is solving the differential equations. The topic is solving differential equations using Laplace transform. Let us take a simple example so that you will understand the method how to solve a differential equation. Once the method is understood, that can be applied for any complicated problem. For the sake of simplicity, I am taking a very simple problem, that is solve y dash minus 2y is equal to e power t comma y of 0 is equal to 1 using Laplace transform. If this using Laplace transform of is not given, do not apply the Laplace transform. You can solve this problem so easily. But here the requirement is solve this differential equation using Laplace transform. Solution. Given differential equation is y dash. I have taken just the first order differential equation. The method can be applied for any order differential equation. Y dash minus 2y is equal to e power t. This is number 1, and the initial conditions, this is only one condition, that is one initial condition is, because it is first order, only one condition is given. If it is third order, three initial conditions will be given. Y of 0 will be given, y dash of 0 will be given, y double dash of 0 will be given. Okay. So initial condition is y of 0 is equal to 1. Now after this one, I will tell you how to apply in the case of third order also. I will give at least the outline of that. Beginning for some steps, I will write it very clearly. You see now. Applying Laplace transform on both sides of number 1, we get, what we get now, L of this complete left hand side, y dash minus 2y is L of, on the right hand side, e power t. You can take the screenshot if you want. Okay, now I am just continuing this. What it happens now, that linearity property, you can separate it now. L for this y dash, that is L of y dash. Y is unknown to us and we are finding that y. L of y dash minus 2 times of L of y is equal to L of e power t, you know, that is 1 by s minus 1. Now here comes the main idea, that is how L of y dash is in terms of L of y, that is there in a separate video, that is Laplace transforms of derivatives. In the previous one of the part, I said separately how to find the Laplace transform of derivatives. The heading is Laplace transform of derivatives. So L of y dash is s into L of y minus y of 0. Suppose if it is second order here given, then L of y double dash will be there. And you know that L of y double dash, I expressed in that very clearly in that video. It is s square, because second derivative you remember like this, L of y will be with s square minus s into y of 0 minus y dash of 0. The power of s will be decreasing, that s is gone. And first term only will contain L of y with the power of s equal to the order. And all that remaining are negative terms. And power of s will be decreasing, one thing, L of s will be there, L of y will be there here, and L will disappear. You remember like this, L will disappear, only y will be there, then the differentiation takes place. So if L of y triple dash is there, then it is L of L, okay, s cube into L of y minus s square, power of s is decreasing, and L disappears, you remember like that, y of 0 will be there, then differentiation starts. Again s decreases, so s into y dash of 0. For second derivative, for third derivative, it will end up at second derivative minus s, again s is gone, so y double dash of 0. It is third derivative, it should end up at second derivative. I hope you will be able to tell what is L of fourth derivative. S power 4 into L of y minus s cube into y of 0 minus s square into y dash of 0 minus s into y double dash of 0 minus y triple dash of 0. So the point is, if this first order derivative is there, the expansion is like this. If it is y double dash, then this expansion will be used in the place of this bracket. If it is third order differential equation, this part will be used in the case of that bracket. I hope you are clear. Now coming to the second part, this complete expansion is only for L of y dash minus 2 times of L of y. Y is unknown to us, we are solving it for y. So L of y is also unknown, when y is unknown, L of y is also unknown. So L of y is L of y as this, 1 by s minus 1. Now given in the problem that y of 0 is 1, so this y of 0 I will substitute as 1 and s into L of y is as it is, minus 2 times of L of y is equal to 1 by s minus 1. Now what we do is, we will calculate what is L of y now. We will come to know, at least we don't know y, but what is L of y now? L of y is how much? So s minus 2 times of L of y, that L of y I have taken common, s minus 2, and minus 1 comes, that side becomes plus 1, so it is like this. Now L of y into s minus 2 is s minus 1 plus 1 by, so it is s minus 1 plus 1, so it is only s by s minus 1. Just I have taken, okay, simplification, nothing else, s minus 1 plus 1 minus 1 gets cancelled, that s, so s by this one. So what will be L of y now? L of y will be s by s minus 1 into s minus 2. We do not know y, but we came to know that L of y is this much. So how to know that y now? What is y? We don't know y, but L of y is this much. So what will be y? Y will be L inverse of this. So y will be L inverse of s by s minus 1 into s minus 2. Now after applying L, how we have to take the transform of the derivative? You have to know this from the background previous parts, how to find the Laplace transforms, and from the previous parts also you should know how to find the inverse Laplace transform. So if you know how to find the Laplace transform and the inverse Laplace transform, we will come to know what is that y. The moment we are ready with this L inverse, we are ready with the y. Now if you want, you can take the screenshot. Okay, so the continuation of the problem is just taking this L inverse. So what is this first s by s minus 1? Let s by s minus 1 into s minus 2 is a by s minus 1 plus b by s minus 2. It is by partial fractions. So implies s is how much? A into s minus 2 plus b into s minus 1. Now you can substitute some s value and determine the values of a and b, or the other way is to go by comparing the like terms. So it is s is equal to a plus b times of s plus minus 2a minus b. Okay, so comparing the like terms, what we get? Therefore we get a plus b is equal to 1 because s coefficient is 1, and minus 2a minus b must be 0 because there is no constant on the left hand side. Solving this, we get, if you add up these two, this b and minus b gets cancelled. A minus 2a is minus a is equal to 1, implies a is equal to minus 1. When a is minus 1, substituted here, that goes that side, b becomes 1 plus 1 and b is equal to 2. Once we are ready with a and b, we will substitute it back here. So if you want to take the screenshot. Okay, therefore I am just saving some ink on time. I will substitute that a and b here itself. That a is minus 1 and that b is 2. So we need now the L inverse of this one. So that is nothing but L inverse of minus 1 by s minus 1 plus 2 by s minus 2. So what comes now? That is just separating by linearity property. So this constant comes out and L inverse of 1 by s minus 1 plus 2 times of L inverse of 1 by s minus 2. Now that is equal to minus e to the power of t, because L of e power t is 1 by s minus 1. You know about it, because it is L of e power a t is 1 by s minus a, and when a is 1, it is this one, and 1 into t is t. So when L of t is 1 by s minus 1, L inverse of 1 by s minus 1 will be e power t. So if you know the Laplace transform, you can tell the inverse very easily. Similarly, L of e power 2t is 1 by s minus 2. So L inverse of s minus 1 by s minus 2 is e to the power of 2t. That 2 constant is there as it is. So that is nothing but 2 e to the power of 2t minus e power t, and the left hand side is this, which is nothing but equal to y. So we got that y value, which is the solution for the given differential equation along with that initial condition. Here the specialty of this method is we are not going towards general solution and then finding the arbitrary constants. We are directly getting the particular solution, and there are certain situations where we need to use Laplace transforms only to solve certain differential equations. I hope you have understood, and the remaining parts of this will be posted after some time. There will be some time gap between this, okay? So first of all, you concentrate upon this many parts, which are very fundamental parts, okay? The other parts we'll be seeing in the next videos. Okay, thank you.